Today we are going to discuss about probabilistic maps and different types of localization that are applied, especially in mobile robots. So let us check what is the fundamental thumb rule for probabilistic maps is the probability theory itself. So in probability theory, for determining the probability of A, which is given here, which is probability of A, if A is true, then only the probability will stand true. Prior to that, we have a prior probability theory for A, which is P of R suffix t, which is equal to L, which is fundamentally the probability of the robot R at a position L at a time sequence t. So, in order to determine the position of R, that is the robot's position at a particular position, let it be L. So, this L is the variable which is varying with respect to time. So, in typical practice, we apply the condition of probability, that is probability of A or B, which is generally we know that only if and only if we know the probability of the condition of B. So, you can determine the condition of A. That means probability of A is interdependent on the B, so that we can determine A if and only if we have the condition of B. Similarly, that is in case of probability of a robot, if something is known, that is if sensory inputs are known, if that is I suffix t is already known, if the sensory inputs are known, so the same thing can be represented as P into P of R of t, which is equal to L upon I of t. I is fundamentally the sensory data. It could be an encoder, it could be any typical sensor that gives the data to your input, so that this L will vary, or L will have a unique solution for these sensory inputs. So this is the fundamental probability theory behind this probabilistic map building or probabilistic map approach. So we have a product rule, that is product of A and B, which are fundamentally the probabilities of A upon B. If B is already known, you can determine the probability of A. Similarly, when we give a product, okay, so that is AND of A and B, that is the probability of A and B together. Similarly, probability of A and B also can be possible if we know the probability of B upon A, which is if probability of A is already known, we can predict the probability of B. Similarly, we have a Bayes rule which will give a fundamental probability product rule, that is your Bayes rule, which is also equal to probability of B upon A into probability of A divided by probability of B is probability of A upon B. So that's the fundamental rule. Similarly, when we apply the same Bayes rule to the previous rule which was discussed, that is this part, probability of the robot at time t, which is equal to L upon your I of t. So it will yield the result something like this. So if and only if the sensory data is known, you can update the position L, which has the similar application of the Bayes rule. When we apply the Bayes rule to your the robot's theory, we'll get some equation like this, which is probability of L upon I is equal to probability of I upon L into probability of L divided by probability of I. So if we know at least one possible part in this, we can ultimately achieve the probability of your robot's position, which may be true or may not be true in certain cases. So we'll yield some result, so that result is at times it is erroneous, at certain times it is non-erroneous. So this Bayes theory is fundamentally yielding some result which will give you the probability or a probability function of the robot upon a given area. So there is one case study about a Markov localization using topological map. So topology, as I discussed, it will branch upon into different possible ways for entry and exit in particular closed room environment. In Markov localization, there is a typical robot which it is named as Dervish. Dervish robot has a computing system on top, some wheelbase and some encode data and then sensors which will find out the distance, and this Markov localization and the topological map approach is being tested on this. So let us check what they have tested exactly. In this topological approach, if you just consider this particular room, it's a line based diagram where you have two entries into two different rooms, one room that is R1 and other room R2. So the approach would be something like this. H is the entry area, so you can make the robot to pass into this passage. After reaching this R1, that will turn up to two results. Either it can go to H2 or it can enter into R1. So there is two possible solutions in this case, which is represented in the same topology here. Similarly, after reaching H2, there is one more possible solution, whether it can get into this R room 2 or it can move on to the H3. So this robot was tested for this typical probabilistic approach. So in this probabilistic approach, the topological map played a very typical role, and this typical map has been builded in an office environment, and it was very successful in this case. So using this case study, what ultimately we can learn is any typical probability approach can be made in a robot in order to determine its position over a given period of time. So they have derived some metrics for nothing detection. If it is a wall, it has taken 0.70 seconds. Whether the door is closed or not, it has taken 0.40 seconds. Door open or closed, door open condition 0.05 seconds. So that means they have given a typical map for each and every possible solution. For example, in the for case it is 0.30. So like this they have determined individual possible things. So if you could check if the door is open and it is yielding a result 0 because there is a wall there. So that means whenever the wall comes, door cannot be detected. Similarly, the other possible conditions. So like this they have derived multiple solutions for multiple cases in case of a topological map approach using Markov approach, that is Markov localization technique. So let us move on to the next part. Fundamentally, when you're dealing with localization, I have given a fundamental case study. So localization is nothing but a robot should achieve a solution about its position. That is what the localization upon a map. That means you are localizing a robot on a map. So if you have to understand this topic, we have to like go deeper into it. So let us check any typical localization technique especially requires some sensory data and some error, and when it is applied to a typical filter, how it will give you an optimal solution is ultimately. So that means you are optimally reducing the possibility of error in any typical localization technique. So the best possible solution which was universally accepted is a Kalman filter. So Kalman filter, the fundamental diagram is shown in this case. You have a system, let us say this is a mobile robot, and this robot has some outbound errors or could be system errors. So the system errors are considered in this case. So it will give you some measuring data. So that measuring data which is obtained or observed is fed to a Kalman filter. So the Kalman filter will give you optimal solution. This optimal solution is basically the state of the robot. So the state can be varied by the control. So it's a continuous loop. So first, we'll consider like let us say the sensory data have two variances. Let us say Q1 and Q2. So these two are variances are fundamentally two sensors which are predicting your state. For example, a laser rangefinder is used for determining the position. Similarly, one ultrasonic sensor is used for determining the position. So these two sensors they have yielded two results which has some variance sigma 1 square and then sigma 2 square. So when you apply a weighted least square method, that means when you define each and every weight, you define a weight for one particular output and then secondary weight for another output. So once you give a weight, that becomes a weight function w suffix I, and if you just summate based upon these weights, so you will yield a result that is for Q, that is S is equal to sigma I is equal to 1 to n and Wi Q cap minus Qi whole square. That is a weighted least square that is obtained from these two fundamental outputs. When you want to derive a minimal error, that means the minimal error means the difference between two sensory data should be equal to 0. So when you are defining it to 0, the whole equation should become 0. That means the partial differentiation with respect to Q, which will yield the weighted least square sum, which is equal to 0. So this is the secondary part of your Kalman filter. That means you define a variance and then you derive the least square of those two sensory data. Ultimately you summate those two sensory data and then it has to be equated to 0. So upon equation to 0, what we are ultimately going to derive is we are going to derive one fundamental thing, that is this part, which is Q. So upon equating to 0, we'll ultimately get Q cap. Q cap is nothing but weight of the first or the reading from qi divided by weight itself. So that means you will ultimately take out the weight. So that means the weight is also a function of your variance. That means as the variance increases, the weighted value will increase. Further, upon solving this q cap, which will yield one more result, that is a summation of q2 square divided by q1 square plus q2 whole square into q1 plus it is sigma whole square divided by sigma 1 square plus sigma 2 square into q1 plus sigma 1 square divided by sigma 1 square plus sigma 2 square into q2. That means the individual variances and the reading and the individual variances and the secondary reading. So ultimately this term technically should be equal to your weight. So upon further solving, we'll get sigma square, which is equal to sigma 1 square into sigma 2 square divided by sigma 1 square plus sigma 2 square. So ultimately the q cap is a function of q1 plus sigma 1 square divided by sigma 2 square plus sigma 2 square into q2 minus q1. That means whatever the fundamental readings we got, we have to sum it and then multiply and then add it to q1 itself. So that will ultimately yield a q cap. So what is this q cap and how does it vary? So upon final solving, we'll get a density function which is very minimal in nature. That means the function of q in this case, if you can just check, which is very less in nature. That means your variance should be as less as possible. So that equation can be defined here, which is a function of q, which is equal to sigma under root 2 pi into exponential of minus q minus mu whole square by 2 sigma square. So that is the fundamental equation which will yield the output of any typical function in this case. So when upon fusing the density functions, you will yield this typical equation. So the final equation that defines your Kalman filter, that is x cap of k plus 1. K plus 1 is the state, that means your initial state and the next state, which is equal to x cap k plus k into k plus 1 into z into k plus 1 minus x cap. So this equation is the final equation, out of which this k suffix k plus 1 is defined as similar variances, which is in terms of the k. So sigma k square would be equal to sigma 1 square, sigma z square would be equal to sigma 2 square. Fundamentally both are equal, but we have added one more component called as z, which is clearly shown here, which is sigma z square is equal to sigma 2 square. That's all about your Kalman filter. So let us move on to application of the same Kalman filter to a mobile robot. Is you need an encoder for this, and then you have a map database which will feed all the continuous data values onto the prediction part. So prediction part is something what we have done here already, that is sigma k plus 1. What is the next state in this case? That's the prediction. So that part is that part alone is this one. So you have a map and you have an encoder. So both the data are fused, and then position and prediction observation has been done. After this, which will match with your some already onboard sensory prediction. For example, you have one typical space, and then you have onboard, you have some sensors. So the prediction and your actual onboard sensors are matched, then it's okay. So the estimation is okay, fine. And there will be always some offset, but this offset can be normalized. And the output of this matching case structure would be given to an estimation fusion, and then it will be again feedback to your estimation or the position estimate part. So whatever the actual onboard sensors in this case will give you always a raw data. So this raw data is compared with your prediction data. So ultimately it's more or less like you predict the data, compare it with the onboard sensors. So that will yield one typical fusion result. So that fusion result is again continuously checked. So so the mobile robots applies a typical methodology like this. So let us move on to the next part. And there are some fundamental examples for localization system, globally unique localization. The best part for this is GPS. I don't prefer to explain this part because everybody knows the working of a GPS, but I'll discuss upon the position beacon system, and then and followed by a route based localization. In case of a position beacon system, basically you require a beacon that will observe your robot. So you have a base station here, and this base station will have multiple ultrasonic sensors. So these ultrasonic sensors will tell you like different positions of your robots. For example, robot 1, how much distance it is located with respect to the distance of the second robot. So that's all about a position based or a beacon based localization. Coming to the part of a passive part of the same, you have some small towers which are generally passive, and then they are retroreflective. So these retroreflective sensors will be fed by one sensory input. Let us say it's a laser beam which will rotate in 360 degrees. For example, it is tending to move towards this, so obviously there would be a distance reduction from this part based on the reflection. So that's all about a passive reflecting system, which is fundamentally used in non-contact applications or non-contact mobile platforms. So coming to the next part, which is a SLAM. SLAM stands for simultaneous localization and mapping. So you know what kind of localization you are following. Simultaneously you map it onto your the map which you have already built or pre-existing map. That means, or you create a map upon the localization. Both are possible in case of SLAM. SLAM technique is very tedious process. It requires a lot of sensory data. So the sensory data, not only you require the sensory data, at times you require the map data. So let us check what happens in case of a stochastic map technique, which is fundamentally used in any typical SLAM based application. That means you have a map. So this map is being developed by certain inputs. So that inputs, let us check. So let us start the fundamental part about the SLAM. You have an encoder, it will give you some data which it will predict, and it will match with your onboard sensors. So upon fusion, you will get some data. So that fused data will be refined. It will be refined in typical way that the credibility, that the trustworthiness of your position is more. And then, for example, if you are moving on a very uneven terrain, so that terrain data can be added as a new feature. And this new in certain cases certain features are not there. For example, in case of mobile robot, if the sensory data is Z, which is generally not required, so which will continuously feed the data which about the Z axis, so that data can be deceased, or it can be completely removed. So any offensive features that are existing in a map can be removed, and then this complete data will be fed on to one typical station which can continuously take up the data, that is called as map. So this map is again matched with your the prediction part. So this prediction part will again check for any changes in the map. So that means you have a simultaneous process of map building and localization together. So this is applied where you require where you require the terrain is unknown, where the position of the robot is unknown, and your terrain is whether it is feasible for some application or not can be identified for this particular SLAM technique. SLAM technique generally is applied where you don't know about the map, and map has to be built very newly. So in those cases only generally we prefer with SLAM technique. So that's all for the lecture today. Thank you. Thanks for watching.